voice has been disappearing regularly, so if it happens, I'll just take that and use it. So I was told it was for a general science audience, but I noticed there are lots of professionals here in the business of proving theorems, so I hope that some of the talk doesn't get to be boring. Okay, so it's somewhat historical, what I'm going to talk about, and philosophical, and all the opinions expressed are those only of myself, and don't represent any of the institutions that I'm supposedly affiliated with. So we all know Cavalieri. He was the developer of Cavalieri's principle for doing integration, and this was his opinion that, at least in the 16th century, that rigor was not the affair of mathematics, it was the affair of philosophy. So it was a very different view of where rigor belonged. So again, this is partly because I thought it was a general science audience. So we all know that mathematics had its origins in things like measuring fields and exchanging goods and casting astrological charts and things of this nature. And this led people to start to develop ideas of numbers and geometry. And at some point, people started to notice, I guess, that there were some things that kept happening over and over again. And they decided there was some reason for that. And this led to this idea of theorems or statements that could be proved. But I think probably in most cases, the idea of proof came rather late. People just accepted things. And on the other hand, there were these people who eventually just couldn't accept things until they saw proof, and they developed the notion of proof. And I was discussing this point with Percy Deicht just a couple of days ago. And I think that the real truth is that in order to become a mathematician, you have to have this obsession with the idea that things need to have a proof. If you aren't obsessed by this idea, then this isn't a very appealing profession, maybe not even possible to do it. So, again, this is a slide mostly expecting a non-mathematics audience. So, as a mathematician, as Yuri's indicated, I've had a lot of interactions with non-mathematicians, maybe more than most mathematicians. And so I talk to them sometimes about what I do, and they're very surprised by this. They're surprised that anybody does this, that anybody sits down and worries about axiomatic proofs of statements that seem plausible, if not obvious. So it's a surprising thing that mathematicians really continue to do this stuff. So a lot of people think of mathematics as something from a long time ago, and we just use these tools today, and who knows exactly where they came from. So I think everybody is aware that in mathematics there's at least two very distinct cultures. So there's a large body of mathematicians today who I would call inward-looking. And these are mathematicians who are mostly interested in the internal development of mathematics, and usually a very small subfield of mathematics. And they're largely unaware and they're largely unconcerned whether these things that they're developing have anything to do with anything outside of the subfield that they work in. And for these people, I don't think the question of why prove theorems ever occurs to them, because that's all they do. They prove theorems, and they develop tools for proving theorems, and they develop new ideas, and they try to find new theorems to prove by drawing analogies to other fields, mostly of mathematics. And so this question has nothing to do with that group of mathematicians. And then there's another group of mathematicians who I would call outward-looking, and these people look to the outside world for motivation and for problems and for things that ask for mathematical formulation. And they're not that interested necessarily in the abstract development of the field. And there are instances of, well, I'm saying that this is a very different motivation. I'm still talking about the first group here. So the people in the first group, they're not interested in the outside world, but occasionally I think something that they develop becomes just important, just unexpectedly important. Like, I have a few examples here. So we all know that Albert Einstein was very fortunate to meet this fellow Grossman, who was a differential geometer, and who could tell him about all these marvelous developments in this new subject of differential geometry, which turned out to be exactly what he needed. And then another example I could think about, I thought of, was elliptic curves over finite fields. Now that certainly was developed for purely internal reasons. I think the whole development of arithmetic over finite fields, the whole idea of finite fields is something very abstract. And then quite by surprise maybe, these turned out to be just the tool that they needed to develop error-correcting codes and to do all kinds of cryptography. And I think that was a remarkable outcome. And maybe the last one here is from geometry, is the theory of characteristic classes and secondary characteristic classes. Again, very abstract things, very mathematical things, and that have now become very popular, at least in quantum field theory. They become very important subjects. And again, sort of an unexpected development. But I think overall, the transition from purely abstract mathematics to an application is an unusual circumstance. And maybe it's because it requires people who have a very sophisticated knowledge to make that kind of transition, and that's an unusual circumstance. Okay, so then there's this other community of mathematicians who are looking outside of mathematics for inspiration. They're looking to applications of mathematics like physics or chemistry or economics. And I think that if you look back historically, this was certainly the dominant culture of mathematics probably through about 1950. I think there was a big change after the Second World War in the way mathematicians saw their subject. And certainly most of mathematical analysis, differential equations, probability, statistics, all these things are really the outgrowth of trying to use mathematical tools to solve practical or somewhat practical problems. So in this context, this question of the value or even necessity of proving theorems, it certainly arises. And if you deal with physicists and if you deal with non-mathematicians, they really wonder why you do this. Why do you spend your time doing this? It looks like awfully hard work. And then, frequently at the end, what you proved is something they consider to be obvious or not even interesting, because that's not really the problem that they need the answer to anyway. So then, maybe today what I'm discussing has to do with the value to non-mathematicians of statements having proofs. Not so much, of course, the value to mathematicians is almost obvious, but is there any value to non-mathematicians of proving theorems? Okay, so I want to talk about some examples from history. So here we have a tablet, and I have to say Wikipedia was a great resource for preparing this lecture. It's supposed to be Babylonian from 1800 BC or thereabouts, and it's a list in some form of Pythagorean triples. So integers that satisfy the relation a squared plus b squared is c squared. And probably, one can only imagine that because you could write down so many examples, there are infinitely many examples, and they were pretty easy to generate them, people must have figured out this theorem just by looking at the examples. There were lots and lots of them. And so probably most people just felt like, well, this must always be true. But eventually, even a long time ago, people felt like it needed some sort of proof. And there is a proof of the Pythagorean theorem for the special case of the 3, 4, 5 triangle. And it's from about 2,500 years ago. And here is sort of that proof in the general case, where you construct this square with an inscribed square made out of the triangles. You do a little algebra, and you sum up the areas of the pieces, and lo and behold, it tells you the truth of the Pythagorean theorem for any right triangle. And I think that proof also is very old. And there are many, many proofs of this statement. Now, this theorem led to a significant crisis in the Greek view of the world, in Greek mathematics. Because from this theorem, you were forced to come to grips with the number square root of 2. And the Greeks had this axiom that numbers should be what they called commensurable. That is, they should all be rational numbers. They had some idea that there was some smallest unit, and everything was a ratio starting with that smallest unit. And this was really just an axiom of their worldview. And this was really a problem for them, because they could prove that this number square root of 2 could not possibly be a ratio of whole numbers. And their proof basically was to show that it had to, on the one hand, be an even number, and on the other hand, it had to be an odd number. So it couldn't be a whole number at all. Okay, so Zeno, we've all heard about Zeno, and I learned something when I was preparing this talk, which is that we call this Zeno's paradox. So this is the story about the rabbit runs half the distance, and then he runs another half of the distance, and another half of the distance, and he keeps taking away half, and there's still something left, and this is somehow troubling. So Zeno actually presented this as a paradox meant to be only paradoxical in the Greek view of this idea that everything had to be ratios of things where there was a smallest unit. He was trying to show that this couldn't possibly be the case, that you could always further divide, and that there should be some notion of what we would today call a continuum. Now, Zeno's claim was not accepted, and the Greeks did not have any abstract way to define numbers other than rational numbers. So this was ruled to be just not convincing, that they needed a better notion of number. The problem had to do with their notion of number. So another example was the number pi. Apparently many people suspected the number pi was not commensurable, that it was somehow a complicated number. But actually it's very hard to find a statement where they actually say this, that it's not a commensurable number. But Archimedes had this method of computing pi. He estimated above and below by inscribing and circumscribing polygons and then being able to calculate the circumferences of the polygons. Using the 96th gon, he got that result, which is a lot of, if you think about it, it's a lot of work to go to for a not very precise answer. And apparently that was the method for many, many centuries of computing approximations to pi. And just to give you an idea, there's what the 9-gon inscribed and circumscribed looked like. On the right-hand side there is the 96th gon. And from the picture it looks pretty good, but it doesn't give a very accurate answer. Okay, so Eudoxus, we have all heard of Eudoxus, he resolved this conundrum. And this is what he decided was the answer. He decided that there were numbers, and then there were things called magnitudes. And magnitudes were things that arose from geometrical constructions. And he said, well, magnitudes, they could be incommensurate. That is, they could fail to be rational. But numbers couldn't be. Numbers remained commensurate. So he made this separation between the abstract notion of number and the abstract notion of a length that could arise in a geometrical construction. And I don't think that this served the Greeks very well. So the Greeks didn't really develop much in the way of algebra or effective algorithms for doing arithmetic. And it may be because they had this somewhat faulty conception of a number, that there was something essentially different between magnitudes, lengths and geometrical figures, and numbers. So it took a long time. So my conclusion from that is maybe being too rigorous too early is actually not a good thing for intellectual development, that you kind of run into a wall. And if you insist upon having an axiomatic description of every object you work with, sometimes you get stuck. And it takes, 1,500 more years before anybody figures out what the next step is. So as we know, Arabs developed algebra, they developed decimal notation, they developed algorithms for doing arithmetic. And once I think you had decimal notation and you could write numbers with arbitrarily many digits to the right of the decimal point, then you stopped worrying so much about the continuum. You started to feel like you had some knowledge of the continuum. And I think that was probably a necessary step for the eventual development of calculus. So now when we think of this from the point of view of proving theorems, we realize, okay, so people were using real numbers probably from the middle of the 17th century. But it wasn't until the end of the 19th century that they actually came to grips with the true nature of real numbers. They came to the realization, for example, that there are uncountably many real numbers, but only countably many rational numbers. So you have to wonder then how important it was to have a fully developed axiomatic understanding, even of numbers. They worked pretty well for many, many, many centuries. Okay, so Leibniz and Newton developed calculus in the 17th century, and I think the remarkable thing about calculus was that Newton developed this method for deriving physical laws, which is the method of using infinitesimals. And these laws that he developed were actually really very different from any physical laws that preceded these physical laws. So we compare Newton's physical laws to Kepler's physical laws. So Kepler gave a description for the motion of two bodies under the action of gravitation, and it's these three laws, that the orbit of the planet is an ellipse with the sun at one of the foci, a line segment joining a planet and the sun sweeps out equal areas during equal times, which is what we now know as the conservation of angular momentum. And the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit, which is true, but not obvious. Now, Newton also had a way to formulate that. So Newton formulated exactly, he studied exactly the same physical system where you have a planet of mass m1 and a planet of mass m2, and Newton said, okay, one is located at x1, one is located at x2, and they satisfy this system of equations. So the center of mass doesn't accelerate, that's the first equation, and then you have Newton's universal law of gravitation as the second equation. Now, Kepler's laws is an easy consequence of Newton's laws, but Newton's law is somehow quite a different thing. From Newton's laws, it's not really so easy to say where the planet's going to be in 5 days if I know where it is today. You could say where it is in 5 milliseconds, but it might be a lot harder to say where it's going to be in 5 days. Whereas with Kepler's laws, you could just look at the formula and write down the answer and plot it on the ellipse, and there you go. You have the answer. So Newton had this idea of writing down physical laws that was extraordinarily different as a sort of an intellectual object. So Newton had this advantage, though, that he could write down physical laws for vastly more complicated things. Like he could, for example, write down physical laws for the motion of n bodies under the action of gravity. And again, the problem is, of course, that these laws give you a good prediction over very short times, but no prediction in particular over long times. And I think it's very useful at this point to pause for a moment and go to visit Bob Vanderby's webpage, where he's taken the trouble of finding many, many, many interesting solutions of Newton's laws for small numbers of bodies. So there's the seasonally appropriate law. That's the Star of David solution. I'll show you a few more here. Here is a very interesting one. I can turn them. Well, let's see. Well, in a way, if you can visit this webpage, I strongly recommend it. There's so many good ones here. When you look at this, you realize that the equations of Newton are a very peculiar way to describe a physical law, because the examples that I've shown you should give you some idea that while the equations are sort of a complete description of the physical system, to actually understand any particular case means understanding a solution to the equations. And that's a much, much more complicated problem. And the range of solutions of those equations is almost unimaginable. Just fiddling around, Bob Vanderby has found zillions of them, and other people have found them. And you look at them and you can't believe that there are solutions to the simple-looking equations that are as complicated and varied as these solutions are. And so the problem here is that when you describe a physical system in terms of differential equations or partial differential equations, the properties of the physical system are really inherent in the space of solutions of the equations. And the space of solutions of the equations are a long distance from the equations themselves. So it's easy to write down equations, it's very hard to solve them. So this was sort of the trade-off that Newton sort of discovered, that you could write down laws to describe arbitrarily complex physical systems. But a priori, those laws did not tell you very much about the system. So the real work just begins when you write down the physical laws. So, for example, even the simple kinds of, we would say that these Newton's laws for planetary motion are relatively simple. They're just systems of finitely many ordinary differential equations. Sort of a relatively complete theory of ordinary differential equations didn't exist until the late 19th century. So these laws were written down in the middle of the 17th century. It took about 200 years before people had really fully understood the problems entailed. And for Newton's laws, in fact, I mean, it's still a subject of research because Newton's laws allow for collisions. And it's still a question, what happens when planets collide? 2 planets, I think we understand. If 3 planets were to collide, maybe that's a problem that's still not completely solved. Okay, so a few other examples. Boltzmann equation, it's from the 1840s. So the first proof of the global existence of solutions for realistic models of the scattering matrix didn't occur until 2010.
Excuse me, can I just ask as a physicist here,
Sure.
What do you mean by global existence of solutions?
Global in time.
What does that mean?
Oh, it means that you start with initial data, you have Boltzmann's equation, which is this integral differential monstrosity. And you start with initial data, and then the question is, does this equation here actually, can I prove that it has a solution for all time in the future, into the future? And does that solution, does it not blow up?
So you mean that you want to rule out some classes of singularities that might occur as the solution evolves from some initial data?
Yeah, in effect that. And it took, and actually even today, the best theorem is a theorem that says that there's a little neighborhood of the Maxwellian where you can, if you pick initial data in that little neighborhood, you can demonstrate that there's a solution that exists for all time and converges exponentially to the Maxwellian. That's the best theorem to date.
Pretty good.
I mean, yeah, it took 170 years to prove. So Einstein's theory of relativity, 1915 or so, and then the stability of the simplest solution to that equation was demonstrated in the late 1980s. The foundations of quantum mechanics were quickly completed by von Neumann, 1932. Quantum mechanics maybe 1925, 26. But apparently the physicists didn't appreciate it very much. So there's a very good story that Peter Lax recounts in his book about Friedrich's meeting Heisenberg. And Friedrich says to Heisenberg, that mathematicians are very, very grateful to physicists for creating this marvelous theory. And Heisenberg said, yeah, we can understand that. And then Friedrich says, well, maybe physicists have, maybe mathematicians have made some small contributions to this subject as well. And Heisenberg was a little puzzled and looked at him and he said, well, what do you have in mind? And Friedrich said, well, there's von Neumann who clarified the difference between a symmetric operator and a self-adjoint operator. And Heisenberg said, there's a difference. So it's not so obvious that the physicists really cared. Okay, so quantum field theory is our current theory, and it still lacks a mathematical foundation. It doesn't seem to stop the physicists. Okay, so we see that mathematicians lag way behind physicists or other scientists in most cases, and maybe that's not that surprising because what we're trying to do is in many ways much more complicated than what they're trying to do. 50 years, a century, that's not unusual for the time between the formulation of a theory and the time that mathematicians feel like they really understand the theory. And by which time, of course, physicists are kind of not that interested. Okay, so I would like to talk at some length about the Dirichlet problem. This is a very interesting equation. Of course, the problem is to find the harmonic function in a region in space where the boundary values of the function on the region are specified. This problem is of central importance in all kinds of applications in electrostatics, magnetostatics, gravity, heat flow, Brownian motion. The list is very long. And it's also an archetypic problem of a large class of problems in partial differential equations called elliptic equations. So the model was in common use in electrostatics, certainly by the beginning of the 19th century. I found a reference in 1840, but I'm sure it's much earlier than that. In 2 dimensions, this was the problem to which Riemann attempted to apply Dirichlet's principle in 1857, though not exactly successfully, so we'll see a little. Klein wrote this book about Riemann's theory of algebraic functions in the 1870s, and it is a great quotation here. I've not hesitated to take these physical conceptions, by which he means electrostatics, as the starting point of my presentation. Riemann, as we know, used Dirichlet's principle in their place in his writings. But I have no doubt that he started from precisely those physical problems, and then in order to give what was physically evident, the support of mathematical reasoning, he afterwards substituted Dirichlet's principle. However that may be, the physical method seemed the true one for my purpose, for it is, or at least was, well known that Dirichlet's principle is not sufficient for the actual foundation of the theorems to be established. Moreover, the heuristic element, which to me was all important, is brought out far more prominently by the physical model. Okay, from which we can conclude that Riemann was assuredly the Thurston of the 19th century. That Klein was going to give him credit for these results, whether or not he'd actually proved them. Now, of course, his statement here that Dirichlet's principle is not sufficient for the purpose, well, it was true in 1871 or 2 when he wrote this, but the story, of course, goes on. So the first serious attempt to show the existence of solutions was given by Schwarz in 1869, another approach by Carl Neumann in the 1870s, and Poincaré gave the first general proof of existence of a solution to the Dirichlet problem in 1889. The problem was still very interesting. Hilbert states it as his 20th problem in 1900, and of course people worked on linear elliptic equations until certainly with the 1950s. It was still a big subject of analysis. So it's had a lot of legs. Okay, so why do I think that Poincaré's work is so interesting with regard to this question? So Poincaré wrote a long, long paper published in the American Journal of Mathematics about this question. And in the beginning of this paper, he has a long discussion about why is he doing this work. It has the following sentence. Not only is it usually impossible to solve this problem completely, by which I think he means write down a solution in terms of well-known transcendental functions, but it even requires a lot of hard work just to show that a solution exists. Is such a proof really necessary? Most physicists would say no. So he didn't italicize that, but I think it's notable. 1889, he's even thinking about this question, and he comes to the same conclusion, I think, as most of us would come to today. So Poincaré did in the paper. He proves in detail many properties of harmonic functions. He uses a variant of H.A. Schwarz's alternating method to prove the existence of solutions for regions with smooth boundaries, C1 boundaries. He says explicitly that the technique is crude and not suitable for numerical computation, notwithstanding that today it has become an important part of what are called domain decomposition methods. So maybe in 1889 it wasn't suitable, but today it is suitable. So now, Poincaré had a long discussion about this question about why should we bother proving theorems. So one of his remarks is that analysis should be self-contained, and I say, I add the parenthesis, and logically is self-contained. So he said physicists would argue that the model is derived using sound physical reasoning, and so the properties of solutions should in fact conform to expectations from their physical meaning, which of course is a circular argument. You use sound physical reasoning, but you're asserting that the model does describe the physical situation. So it doesn't prove anything, of course. So a rigorous analysis of the model is the only way to break the circle. The mathematical formulation, if it's correct, is logically complete. It doesn't require any physical semantic interpretation to be fully specified. It doesn't rely on the physical interpretation. Its predictions, its space of solutions to the equation are inherent in the model. So the question as to whether or not it is a good description of the physical situation is a question that can only really be answered by doing an analysis of the model. So Poincaré also notes that arguments from physics, which might be applied in an explicitly physical context, might be inadmissible for some other applications of the same model. So he recognizes that the same equation describes lots of different things. So if you try to, you get to a hard point in the argument and you now say, and this is because if I charge up a body of this type with an electric charge, it's going to have some behavior. It's not going to work if you're actually studying a problem in heat flow. Okay, they have the same model mathematically, but the physical argument then is a lot less compelling. Okay. He then goes on to say, how does one assess reasoning whose rigor is not absolute? May it not be a simple fallacy? When will it be right to say that such a demonstration, insufficient for analysis, is rigorous enough for physics? So really, if the argument isn't logically complete, logically correct, how do you assess whether it's right or wrong? You just say, well, it's my intuition, that's why I think it's right. So it doesn't present a proof. It presents sort of an argument by personality. So then he makes the point that differential equations that model a physical phenomenon have been produced by sloppy reasoning. We only look at them as approximations, and the experimental results, which are compared to the consequences of the theory, are themselves approximate. Why then must we prove existence with complete rigor? Well, I'd say it's exactly why. Because there's nothing completely rigorous up to the point that you've written down the model. So if you want to know whether the model is a correct model, you do have to then study the model itself. The errors in the approximation using derivations of mathematical models are not effectively estimated. And I think those of us who've read physics papers know this, that there are lots and lots of assertions made where we're going to ignore this term, we're going to ignore that term because it's small. But how small is it? And when is it small? Well, these things are never made clear. So I spent a year working in the radiology department at Penn, and I was working in magnetic resonance imaging. And this year I spent a lot of time reading physics papers. And I found it incredibly challenging work because you'd read a physics paper and there'd be a formula, A equals B. And you'd spend days trying to figure out why is A equal to B. And then I came to realize, oh, A equals B does not mean the same thing in a physics paper as it means in a math paper. It just means something quite different. It means, and I think in the meaning of a lot of these papers, what it meant was there's a quantity on one side, there's a quantity on the other side. And I don't know any experiment that I could do where the measurement would give me a different answer on the one side than on the other side. So A equals B. It wasn't a mathematical identity at all. Okay, so beyond that, you can't really imagine, given the nature of these uncontrolled approximations that went into the derivation of the model, you don't have any serious belief that you can really say when the model is applicable and when the model is not applicable. So again, when a more complicated model is needed, and here we have a great quote from Einstein, that things should be as simple as possible but not simpler. But how can you tell when things are as simple as possible? I mean, this is only something that you can tell if you know whether the model you wrote down actually predicts what you observe or it doesn't. Okay, so in the end, Poincaré says that he will work as rigorously as possible. And of course, the paper is entirely rigorous from this point on and is a complete proof of the theorem. And he says, well, why does he have to do this? This is a point we came upon a little while ago. He says, it is always hard for a geometer to address a problem without completely resolving it. So he can't help himself. That's why he's going to do it with complete rigor, because he can't help himself. And I think, again, that's almost a necessary prerequisite for doing things with complete rigor, is that you can't help yourself. Then he said, well, it would be bad for business if we didn't do things this way. And he says, we might need these results for some other purely mathematical question, where the connection to the physical model isn't obvious at all. So, for example, he has Riemann's theory of algebraic functions on surfaces. It relies on the solvability of the same Dirichlet problem in 2 dimensions. So he says it would just not be a good thing for mathematics if we didn't do these things carefully. And I think that's a very important point, that the mathematics done today is the basis for what comes tomorrow. And if we don't address these questions today, it would leave tomorrow's developments without any kind of firm basis. We wouldn't be doing mathematics anymore. So I'd say having a solid foundation is good for everyone. Then mathematicians have a reliable starting point for their research, and the users of mathematics have new boundaries for the frontiers of mathematics, which they can then exceed. So I think that a lot of the development of physics relied upon the fact that mathematics was developing. It was developing at a somewhat slower rate, but they could then go beyond what was known to be true. And if they had never developed those foundations, well, maybe physics would have been stuck, because they wouldn't go too much further beyond what was known. It's a counterfactual statement, I don't really know, but that's what I think. So what about Dirichlet's principle? So Dirichlet's principle, for those of you who aren't PDE guys, says you want to solve this equation, Laplace u equals 0, and you want to specify the boundary data to be some function f. So what you do is you look at all functions that have that boundary data, and you find the one that minimizes the integral of the gradient of u squared over the region. So that's what Dirichlet said would be the way to find the harmonic function. And in the end, it was possible to justify Dirichlet's principle. It basically required the entire edifice of Hilbert space to do it. And even when you had the whole edifice of Hilbert space, all you got were weak solutions. So not solutions in the classical sense, but some solutions in some more generalized sense. And then you had to do a lot more work to actually show that these solutions that you got were classical solutions when everything was smooth, when the boundary was smooth, when f was smooth. But in the end, actually, Dirichlet's principle was perfectly fine. And then Dirichlet's principle goes on to be the central idea and a huge part not just of mathematics, but of materials science and all manner of applications. And you try to imagine where science would be today if no one had taken the trouble to actually prove that Dirichlet's principle was correct. It was something that was considered to be wrong for 50 years. So I think there's a pretty compelling explanation for why, in the end, it's good for everybody if mathematicians do the work that's laid out there for them. Okay, so in addition, these are reasons reasons for proving theorems that I think were all understood in the 19th century, and I think in the last 100 years, some more reasons have come up, and one has to do with numerical applications. So in Poincaré's time, of course, numerical calculations were very primitive. If you were very, I guess, rich and powerful, a room full of people doing calculations on pads, but mostly calculations were done very genially. You had an asymptotic expansion, you could compute a few terms, that was a calculation. But of course today, you could do calculations that are enormously complicated. And when you're trying to use mathematical models to solve complicated problems, you need to have a good understanding of the mathematical model. So just as the transition from a physical system to a mathematical model is a process of approximation, and for these approximations to be successful certainly required a deep understanding of the physics or the physical system or the economic system or whatever it was that you were modeling. Well, similarly, I would say a transition from a mathematical model to a numerical model, a computational model, is a different process of approximation. It's going from the continuum to the discrete. And to design a successful algorithm that gives reliably accurate and approximate solutions, again, it requires a deep understanding of the raw material, which in this case is the mathematical model. So again, this is a reason why analyzing mathematical models, proving theorems about them, is a fundamentally important thing. To get good numerical results where you know that the numerical result is actually a good approximation to the actual answer, required understanding the mathematical model in order to design a computational model. Now, of course, people will say, computation is used all the time to study models that we don't understand that well, like Euler's equation, the Navier-Stokes equation, the behavior of galaxies. All these things are certainly implemented on a computer, and we build supercomputers to do more and more particles and more galaxies colliding. But in the end, of course, interesting results of these calculations remain quite controversial because they are not the results of mathematical analysis, the results of computer experimentation. And so, in a real sense, they're very much like the physical arguments that went into the derivation of mathematical models. They're intuitively appealing, they give some insight, but they're not theorems. They don't prove anything. And in the end, if you really want to understand, you have to prove the theorem. Okay, so a concept that was introduced in mathematics long after the time of Poincaré, or a generation after, was this idea of well-posedness, which was an idea introduced by Jacques Hadamard, a French mathematician who did a huge range of things, from number theory to PDE, and he had this idea of what was called a properly set or well-posed problem. And roughly speaking, a model is properly set if it has a unique solution for each reasonable choice of data, and the solution depends in some sense continuously on the data. So in his paper, Hadamard explains, really to other mathematicians, why it's important to analyze PDE. So it's an interesting question that in 1923, it was not obvious to all mathematicians that PDE was an interesting subject, that you should waste your time studying the existence of solutions to PDEs. So he said this, and I should say that there was a theory that was developed by Cauchy and Kovalevsky, and it applied to analytic equations with analytic data on analytic hypersurfaces. And he was saying here, I have often maintained against different geometers. So these geometers are a problematic group. The importance of this distinction, that is well-posed versus ill-posed. Some of them indeed argue that you may always consider any functions as analytic, as, in the contrary case, they could be approximated with any required precision by analytic ones, which certainly is true. But in my opinion, this objection would not apply. The question not being whether such an approximation would alter the data very little, but whether it would alter the solution very little. And what he demonstrated was that for equations that everybody thought were perfectly benign, that this exact thing was completely false. That you could approximate the data as well as you wanted, and the solution would be approximated as poorly as you wanted. And so, indeed, there was really something to understand here. So, a more modern statement of Hadamard's idea can be found in Courant and Hilbert. They say, a mathematical problem which is to correspond to physical reality should satisfy the following basic requirements. A solution must exist. a solution must be uniquely determined, and the solution should depend continuously on the data. So then such a problem is called properly posed. So whether or not a problem is properly posed relies on finding the right notion of continuity. So continuity, for most people who are professional mathematicians, we all know it's a complicated problem, especially in the context of partial differential equations, where it's a question about continuity in an infinite dimensional context. It's an entirely mathematical question. It can't be answered without a rigorous analysis of solutions to the equation. So that to me is yet another reason why, at least for mathematicians, it's important. But now, I think this is something that's even of interest to non-mathematicians, because this question of well-posedness is the idea that the solution should depend continuously on the data. And what is data in a physical problem? It is the results of doing practical experiments. So now, I ask you, I've collected some data, and I've run the model, and I get a completely different answer. And then should I say, well, the model's wrong? Well, it's not so obvious, because it depends upon the sense in which the model depends continuously on the data. Maybe my data just isn't good enough for this to be a real test of the model. Maybe I actually have a model that's a little bit particular, or I haven't gotten the data to be close, accurately enough computed or measured in the right sense. And so in fact, I haven't tested the model at all by doing this experiment. So this notion of continuity is actually very important when you're designing experiments, to decide whether or not the output of the experiment is a reasonable test of the model. So in this sense, I think this notion of well-posedness is something that's really of interest, not just to mathematicians. It's of interest to experimental scientists as well. Okay, here's a great quotation from Joe Keller. Sometimes engineers and scientists, especially when studying mathematics, criticize this theory, that is the existence and uniqueness theory of partial differential equations. They point out that the physical phenomenon which the problem describes is properly posed so that it is unnecessary to prove it. So in 1978, the same opinion persists among physicists and engineers. What they fail to realize is that the purpose of the theory is to determine whether the mathematical problem does describe the physical phenomenon. It can do so only if it is well posed, because the physical phenomenon is well posed. A more appropriate criticism is that the theory stops with the demonstration of well-posedness, rather than proceeding to the determination of specific properties of the solution. Regularity theory, which concerns the degree of smoothness of the solution, is a first step in this direction. Well, I think I have to agree with everything Joe Keller says, that it's very important to do the work to see whether the model is well posed. But also, I think mathematicians do have a tendency to say, well, we prove the existence and uniqueness of solutions. Okay, the method's non-constructive, so what? Because they don't have enough interest in what the right questions are. And I think my own personal experience of trying to work with really applied problems is that the questions to which applied people want answers to are very frequently, really hard mathematical questions. That is, you like to make some assumptions to simplify the problem, you prove a theorem, but it doesn't answer the question that they're interested in. Because they're interested in a case where those hypotheses, those extra things you assumed to prove your theorem, they just don't hold. So I think a lot of the dismissiveness that empirical scientists have for mathematics is because mathematicians do not go that extra mile to actually prove a theorem that addresses the question that they're interested in. Of course, this requires that you talk to people in applications. Okay, so then the last thing I want to talk about is intuition. So everybody, the alternative to proof is intuition, in effect. I'm saying, we know this is true because we understand this in some intuitive way. But here's the problem. The problem is that we have today, I think, a lot of applications of mathematics where it's really hard to know what the intuitive answer would have been or would be. So for example, stochastic calculus requires, I would say, Kolmogorov's foundational work on probability theory. Calculus, it was really hard to imagine how you would develop that subject on a purely intuitive basis and not get most things wrong, which is very difficult to imagine. For example, a theorem like the contractibility of the unit sphere in an infinite dimensional Hilbert space is it's not a hard thing to prove, but it's a surprisingly unintuitive fact, at least to me. The Johnson-Lindenstrauss lemma, which is loved by people in large data analysis, again, it's a very odd thing. It's another example of a phenomenon that large dimensional spaces are very different from low-dimensional spaces. And our intuition about geometry, mostly it comes from low-dimensional spaces. It's very hard to have intuition about high-dimensional spaces. And you can make assertions, but if you don't prove those assertions, then I don't think there's any basis for them at all. So I think in the end, you have to recognize that there are large application areas where you can't make progress without proving theorems, because there is no intuitive basis for making progress. Okay, so my bottom line is that mathematics is, when you couple it with numerics, it's used to model very complex situations. And without rigorous foundations, it's very hard to have confidence in the sufficiency of the model and the results of approximate calculations. And the level of mathematics being applied, it pushes the frontiers of mathematics. It will always be used in contexts where it hasn't really been established, which is great, right? And this is possible because we have confidence in the foundations. And I think when it's used like this, and it's used to make predictions, and they find, like, for example, the example of quantum field theory always comes to mind, where they say they make these calculations that are accurate to however many digits you want, and you ask yourself, how do they know that? Since they can't do experiments with that many digits, but okay. They like to say this. It does make you believe there must be a theory. There must be a mathematical foundation for this subject, and eventually somebody will find it. And of course, sometimes, as we pointed out a little bit earlier, occasionally, mathematics, which is developed just for purely internal reasons, that is because that's how mathematics wants to develop itself, does have remarkably powerful applications. So those are my reasons for thinking that we should all be proving theorems, or at least some of us, not always, but some of us should be proving theorems. Thanks for your attention.